Hello and welcome to the Rubber Duck Dev Show. I'm Chris.
I'm Cruston.
And tonight, I'm going to talk about Ractors. Okay, I don't even know what those are, but we will be taught.
You know what doesn't know what Ractors are either?
What?
Spell check, because every time I type that thing out, it changed it to a tractor, driving me bananas.
That had to be fun. All right, so before we get into that, how was your week?
Pretty good, although, did some consulting, worked on my product, added some new features. But one thing that drove me batty for about a day, I was doing other stuff to prevent it going full bat mode. But suddenly, I went to run my tests, and any test that called out to something, which I do have some tests that do that, or even it was doing a visit. It wasn't even just calling out. So I was getting net timeout errors, even if I'm just in Capybara or whatever, doing a visit to one of my own internal URLs in the test, it was failing with a net timeout from Ruby. I'm like, what the heck is this? And then, so I started going down the rabbit hole. I'm like, okay, did I install some gem that's doing this? Is the Ruby version, is there something different there? And, once I eliminated that as a potential cause, I'm like, or looked into other projects, and other projects were having the same issues. I'm like, okay, is it my machine? So I'm looking at, is there something wrong there? Let me restart it. That didn't help. Let me shut it down. Let's start it back up. Let me apply patches. Let me, anything and everything. Nothing worked. So then I'm like pulling on my laptop. I'm like, all right, does anything work here? Nothing was working there. Then I'm like, is it my bloody network or whatever? So I go and I reboot the router, and tra-la-la, everything works.
Oh.
Now I will say this, nothing else was broken. I could use web browsers. I could do my patches, my updates. Everything worked but Ruby.
That's
so I'm
bizarre.
Like, what is it? No offense to the Ruby community, but what is it in Ruby that there's a networking issue that causes it to break, but nothing else?
That is weird.
I have seen some issues where someone was trying to update gems and IPv6 wasn't working. And I don't know if it was having problems falling back to IPv4. I don't know. And the message was just nondescript. It just said net timeout error. And that's pretty much all it was. So it's...
Gee, thanks, Microsoft.
Well, this is Linux, but...
I know.
Yeah, so... I had nothing to, there's, for some reason, it wasn't communicating over the networks. I mean, so of course that makes sense, that error message, but yeah, I'd love to know if anyone in the community or in the comments section knows what could potentially cause this. I'd be grateful to know, because, that's a number of hours of lost work.
Yeah, that doesn't make a lot of sense. So I have spent the majority of my week working on the Ruby 3 upgrade of our core systems, core projects. And really what most of it has boiled down to is the parameter changes, the double splat. So it's not difficult, it's just very tedious.
Yeah.
Going through and finding all those places and fixing them and waiting for the test to run to make sure I haven't missed anything. And then, so it's just a tedious process, but it doesn't seem like anything's breaking other than that. Everything I've run into.
You deploy.
No, of course. Everything I've run into so far is because all I changed was upgrading from Ruby 2.7.2 to 3.0. Everything so far has just been the double splat fix.
So you didn't have any gems that, or I guess it sounds like you guys try to keep your gems up to date, so there wasn't anything that was.
Yeah, I mean, there were actually a couple of internal gems I had to update because they needed the double splat as well. But it's, it hasn't been bad. I think there was one gem that I needed to update, but that's because it was kind of out of date anyway. We hadn't updated it for a little while. So it hasn't been a bad process, but I think we're actually going to talk about that whole issue next week, because while this was introduced in Ruby 3, it was actually in deprecation warnings in 2.7. It's kind of a confusing thing to understand if you're going into your code and trying to figure out, all right, which things do I have to change? So we'll dig into that next week and hopefully get some better understanding of it. But tonight, Sensei, teach me Ractors.
All righty, please put up the presentation and next slide. Thank you.
Here we go.
Okay, so go ahead and do the warning. So the first time that you start using Ractors in Ruby, and this is became available in Ruby 3.0, and it's considered experimental. So the first thing you'll see is this message, quote, Ractor is experimental and the behavior may change in future versions of Ruby. Also, there are many implementation issues. So basically, they're saying don't use this yet. And it also includes 3.1. So the exact same message as 3.0. I mean, I hope there's some forward movement on this because I really like where they're going with this. And you'll see that in the presentation. Okay, do that.
But so it's essentially it's not production ready yet.
Right. In presenting that, because as soon as you say Ractor new and start doing stuff in the log, well, in the console at least, it gives you that message. So clearly it's considered experimental. All right, so let's talk about the problem on why they kind of are going down this route. So Ruby has a global VM lock. So VM meaning the virtual machine. So when you're running Ruby code, there's a global lock on how many threads can run at once. And now prior to Ruby 1.9, you may have heard this called the global interpreter lock. So it was a global interpreter lock, but because we have more of a proper VM now, since Ruby 1.9, the proper terminology is GVL, or the global VM lock. Okay, next point. So what this basically means is you cannot run Ruby code in more than one thread at once. So basically another way to say it is only one thread in a Ruby process can hold the GVL, or the VM lock. So I stated that as the problem, but is it much of a problem? Because the reality is that, like this says here, if your work requires a lot of I/O, like you're calling out to a network, you're writing stuff to disks, you're doing database access, other threads can do work while the thread can wait on the I/O. And that's kind of how Sidekick works in the next point. That's why Sidekick works well, is because it is multi-threaded and other threads can be doing work while other threads are waiting for disk access or database access, network jobs, etc.
Right. So
most jobs use a fair amount of I/O.
So kind of right now, Ruby's answer to multi-threading is background jobs.
Well,
in a manner of speaking.
I would say it this way: their answer for production stuff today, their answer to concurrency is threading. And if you want to do jobs and do jobs efficiently, not necessarily the Ruby core team, but I'm just saying most people using Rails and whatnot, what they've identified as the best way to do background jobs is Sidekick, which is threaded.
Right.
Excuse me. And that's also why Puma has become pretty popular, because Unicorn is process-based, Puma is thread-based, and because you can, depending on what you're doing, it does still wait on I/O. Puma can give you a little bit more performance because it leverages that multi-threadedness. So how much work can be done in parallel? That's kind of the question, because that determines how fast a speed up you have based upon the number of, say, units that are doing work. So there's something called in computer science Amdahl's law. I'm not sure quite how to pronounce that, where it basically says your speed up that you get by adding more, could be processors or threads, whatever it is limited by what must be done serially. So basically, the more stuff you can do in parallel, the more processors you use, the faster things get, which is natural conclusion. And the next point is that, and there's actually, Amdahl's law is actually, there's a function. So you can actually plug in parameters into a function to get what your speed up will be. And there'll be links in the description for all of this stuff, or at least on the website for references where you can look this up and see what the function is. But like one example of it, if 50% of the work you're doing can be done in parallel, and let's say 50% of it is IO work, calling out to a database, calling out to a network service, is 50% of the work is that way. If you break it into, if you have like 10 threads or 10 processes, whatever, only gives you a doubling in performance as opposed to a 10x performance. So basically you would think that, hey, if you want to be able to add 10 times the number of processors to something and get 10 times the work, well, that can only happen if you can do all that work in parallel. Once you have to do something in parallel, some serial, it breaks down. So the more things you do in parallel, the faster you'll get, adding 10 things, getting that 10x result. So the last question is, how do we get the 10x? And that basically, everything needs to be in parallel.
But the problem is you've got a critical path that things are dependent on other things finishing first in most cases.
Yeah, that could be true. Although if you are talking about people accessing a web server for, if you could do everything in parallel, you don't have to wait on each individual person asking for a particular web page.
Oh, sure.
As an example. All right, so an answer to get to 10x is Ractors. So Ractors, and this name is basically Ruby Actors, allow you to go full parallel and use 100% of every core in your machine. Now they do this by each Ractor getting its own VM lock. So before, every Ruby process only has one VM lock, and it shares it amongst threads. Whereas what a Ractor does is it gets its own VM lock, and a single Ruby process can have multiple Ractors. All right, so I'm talking about these actors. So what are actors? So the next point is basically it's a system of independent processes. Now, they're not really operating system processes. Ruby, I don't think has a terminology for them. I use processes here as the terminology because that's what Elixir or Erlang uses, because Elixir and Erlang use the actor model. Essentially, that's how they do their whole infrastructure. Everything's pretty much an actor. Anyway, there are these independent processes or primitives that can send and receive messages, kind of like an object in Ruby, but each has its own memory space. So there you can see the advantage is that when you have your own memory space and you're not sharing things, you can do things in parallel much more easily. If you have something shared, you're going to have to have locking going on.
You have to wait in line.
Exactly. If you're accessing something that's shared, you've had to introduce locks, and now you've introduced waiting. Yeah. Whereas the actor model avoids that by having stuff in parallel as much as possible. Now, each actor has its own address so that actors can talk to other actors, and a mailbox to receive messages, and it serially processes those messages asynchronously. So basically, one actor sends a message to another actor, and then it does something else.
So it's serial asynchronicity.
Yeah.
What?
What that means is actor A can send a message to actor B, and now actor A doesn't have to wait for that message. It can immediately start doing something else. And that something else is probably looking in its mailbox, getting the next message. Whereas Ractor B received that message, it doesn't have to send a response or it does its work when it's come down to the proper point in its mailbox queue that that's the next message. It does that work and then does whatever it's supposed to do next. Maybe it sends a message to some other actor or sends it a message to the one who sent it the work to initially be done and say, hey, here's the result.
Wait, so how is this not SOA?
Well, this came before SOA.
Okay.
But maybe it is.
So SOA is kind of an example then of what these actor models are. In a general sense.
Maybe, I don't know. I mean, I learned all about this just from learning Elixir, etc. Okay. And each actor has its own internal state. So this makes sense from a, like, again, Elixir, their processes, and they have their own memory space that they can access, and they can store things like accumulate things, or do something different based upon future messages and things of that nature. So that's kind of what the actor is. And in terms of the terminology of talking about the actor models, they talk about these 3 different ways in terms of what actors can do. And go ahead and put all of them. There's 4 messages here. So they can send messages to other actors, which I mentioned. They can create new actors. I don't know if Ractors can do this yet. I'm assuming they can, but I didn't see some of those implementation details because this is really just the theoretical what actors can do. Designate what to do with future messages. So, they have their own memory space to store things so they can change their behavior for future messages. And the last one I've added because, yes, they do work. They can process things. They can, talk to databases and things of that nature. So that's one I added in just for completeness because I'm like, well, fundamentally, actors do work.
Well, so this brings up the last slide. One of the things I was thinking is, if they're serially calling each other. So actor
well,
A,
they're not serially calling each other. They are looking in a mailbox and serially processing it.
Right. But so actor A can call actor B.
Sure.
Say, hey, Mr. B, I've got some things here. Here's a thing that you got to do, and you're good at this thing. Do this thing.
Yep.
Right. So actor A's processing of its messages each take 20 milliseconds. The thing it keeps asking actor B to do is taking 3 seconds each. So at some point, actor B gets backed up. So then I was sitting there thinking, well, okay, how is that going to help me if I'm still at some point waiting in the same line? I've just moved the line across the street, right? But if actor A can say, hey, Mr. B, you're too full, I'm going to create another B. If it has the capability of doing that, that solves the problem. But as you say, if Ractor doesn't support that yet, then I'm back to, what does this buy me?
I mean, it may, I just haven't looked at it yet.
Right.
But I know, again, this is I haven't looked into it a lot yet. And there were relatively sparse examples of this. I mean, I found a fair number, but in terms of the example, I don't recall seeing an example of a Ractor creating a new Ractor. Presumably you can do that. But at least with Elixir Erlang, the result, maybe you send it to Ractor A, maybe Ractor B doesn't do the work, but is a queue, and it instantiates new Ractors to give that piece of work that then gets returned to it, then it returns to somewhere, so you can develop any kind of architecture that you want with regard to them. All right, so that's enough talking. Let's look at some code.
Whee!
So This example is from this is a modified example that was included in the release notes for Ruby 3.0. And in it, they used something that it's called a talk function, TAK, or this is a terrarii. Basically, this function is doing recursion. And they use this as an example to test the recursive capabilities of CPUs. And the reason why they used it is because it is all CPU processing. So there's no waiting. So there's no waiting for IO. So we want to really look at just full processing, because here it's very visible to see what the difference between threads with a global VM lock versus Ractors. And in the example in the Ruby 3.0, they just looked at Ractors, but I also wanted to look at threads. So what this basically is doing is like line 9, and the code is identical, I should say, between line 8 and line 19. These blocks are identical except for line 13 and 24. One I'm using Ractors, one I'm using threads. And on line 14 and 25, you have to essentially wait for all Ractors to finish and resume control to the main thread essentially by using the take, and that basically takes the last value a Ractors produced. But in threads, it's called join. So you're joining back to the main thread. That's how I understand that.
So same functionality, just different syntax, essentially.
Right, right. And in terms of like line 9 and line 20, for the threads, you'll see in a minute here, I only did 2, 4, and 6 iterations, whereas I went up to 12 iterations of the Ractors. Now, the reason I went up to 12 is because I was testing this on a 6-core, 12-thread, or 12 hyper-threaded CPU. So that's why I went up that high. And essentially what this does is like line 10, it just does that function multiple times in sequence, so sequentially. So it's going to run it 2 times in sequence, 4 times in sequence, 6 times, so end to end. So essentially just one processor or core is going to be processing this, and how long does that take? Whereas the line 11 and line 22, it breaks either by Ractors or threads, splits it out to multiple Ractors or threads to do the same work. All right, so if we go to the next slide. So this is something I wanted to show. So this is indication of my CPUs and why I have, essentially there's 12 CPUs, so it's 6 cores, 12 hyperthreads. And this example is the CPU results of 4 threads. Now you'll notice that there's no processor that is 100%. And the processors, like if you look around the 5-second mark, the first tick mark from the right is at 10 seconds. So imagine around 5 seconds, you can see maybe it's around 25, 30% CPU usage. So what that means is when you do something by threads and you have just processor work, no IO waiting, it's essentially splitting. Basically, if you run it as one thread, you'll get 100% of a CPU. If you do 2 threads, you'll get 50% of the CPU because the lock's happening. So those 2 threads are in contention for that lock trying to do work. If you go to 4 threads, now each thread is only using 25% of its capabilities. So that's what I'm saying is that now if they had IO to wait on, then they could do more work in that process.
Right.
So let's look at the next slide. Now this is an example of 6 Ractors. Now we didn't do 4, but it would look pretty much the same. You'd have 4, say, call them virtual CPUs up and around 100%. Now you'll see this bebopped all around here. The lines are going all crazy. But if you look at the bottom, you can see, like on the left column, CPU and CPU 5, they're at about 100%, because again, they go up and down and they trade places. So that's about 2 in that first column. Let's say the 71% is another 100% essentially, or it's transitioning. So that's a third, 3. The next column, the third column, where you've got 1 at 100%, that's 4. And then the right column, are you able to move your head just a little bit? Is that? Yeah, so you got 196. So those are the other two, the other 6. So essentially you have all 6 cores doing 100%. Although it's hard to tell here because they're trade in and out like crazy.
Right.
But if you go to the next slide, you can see the 12 Ractors. Now everything's 100%. So it's able to work at 100% utilization. So that's why I'm saying how Ractors allow you to go full parallel.
So you're using all the hardware in this case.
Yeah.
You got 12 threads, 12 Ractors, each one on a thread. They're pumping.
Yeah. Well, each one on a thread. It's one thread, but 12 Ractors.
Yeah.
Because it's only using the main thread. There's no threading going on, presumably.
Well,
or however they implement it. I don't know how they implement it.
I should have said core.
Yes.
Core.
Yes, each one on a core. All right, so now that we've seen this example, because there's a little bit, and then it gets a little bit more interesting when we look at actually the numerical results. So if you go to the next slide. Okay, so what we're looking at here, let's look at line 2. So what that means is the 2 means that's the number of iterations. Sequential means sequentially. And the amount of time spent in user system and the total CPU. But what I think we should focus on is the real, because that's the real clock time that it took to process. So it took about 30 seconds to do that talk function twice, 2 times. If you look at the threaded, it took 31 seconds. So essentially the threads, when you don't have any IO waiting, just full processing, it takes the same amount of time as if you have 2 threads to do it sequentially twice. Now, when you look at the Ractor, it takes half the time. So it's able to use 100% of those cores essentially. Now, if you go down to 4, you can see the sequential doubled, so it took 60 seconds. Same thing with the threads, no difference. And again, the Ractors essentially scaled linearly. It put it across 4 cores, so it does twice the amount of work as the 2, because it's doing 4 iterations, but it still only took 16 seconds because it split it across 4 cores.
About a quarter of the time.
Yeah, and then the same thing with 6. So you'll see the sequential took, again, 3 times as long as the 2, 3 times. Same thing with threads, but the Ractors, not quite as much, but it's pretty much scaling linearly with the number of cores. And this is, I'm referring to line 11. It's at 17. And then you hit 8. Now here I dropped the threads because the threads are the same as sequential, so it doesn't really matter. So sequential took longer, of course, but now the Ractor, now you're starting to see it break down a little bit. Now, why is it breaking down? So I have a 6-core 12 hyper-threaded machine. What that means is I still only have 6 cores, but what it does, it has extra address space for storing things. And how the hyper-threading works is that it basically uses that IO waiting to basically timeshare that core.
But you still got some of these Ractors waiting in line with each other.
Right, because it's essentially one core is trying to run 2 virtual CPUs. And it runs those 2, how it runs, this is my understanding, it runs those virtual CPUs by waiting on IO. But with this function, there's no waiting on IO. So your performance starts getting worse. So much so that when you're at like line 21, when you're at 12 Ractors, you'll see it takes 31 seconds. Well, it would be just as efficient to run line 11, use 6 Ractors twice, like run 6 Ractors and then 6 Ractors again sequentially. That'll be a total of 34 seconds. So that's very close to the result of trying to do 12. So it's basically, Ractors are great or are scaled linearly when you're talking about core count.
So
but
so
not
the
but
sweet
not about
spot
hyperthreading.
so the sweet spot is number of Ractors equals number of cores, not number of hyperthreads.
Exactly. Exactly. When you are talking about things that don't have
IO.
are not waiting on IO.
Right. So
Yeah.
there's no fudge room in there for them to, hey, I've got to wait my turn in line on some other
Exactly.
things, so you can go ahead and go do your thing and then start waiting, and then I can take.
Yeah. At least that's my interpretation of these results. If people looking at this have another conclusion, feel free to put them in the comments. So anyway, so that's why I went up to 12, because I was looking at this. It was like, what's going on? I was like, oh, that's probably with this. Okay, so how do Ractors do this? So if you go ahead and give that. So basically they have their own VM lock because they don't share state. If you go to the next one. And essentially mutable state is the enemy of concurrency, because again, whenever you're going to introduce a mutable state, then you're going to have locks if more than one person is trying to interact with it. And also, I mean, I think async message passing helps as well, as then the last comment. So for example, in terms of async message passing, this is kind of what we were talking about before. You could send an actor a message and tell it to send a message when it's done, and then you can go keep on doing other work. So I wanted to talk a little bit, and I've covered this before, where we're talking about object-oriented versus functional programming. So in Ruby, you typically hear everything is an object. Well, in Elixir or Erlang, everything is a process. But that process is not an operating system process, and it's an Erlang process. Or another way to say it is that essentially everything is an actor. That's how they do the whole architecture. So if you go to the next slide. So what's an actor in Elixir? Like I said, it's not an OS process, so it's not that heavy. And it's not even a thread. It's at a more granular level. So like I said, it's an Erlang process that runs on the Erlang VM. Now, they're kind of similar to talking about Ruby fibers. So Ruby fibers are not threads, but they're a component of a thread. So it sounds kind of similar. And like after the next show, I kind of want to talk about Ruby fibers, because my understanding with them is that they are still constrained by the one VM lock per process, whereas Ractors are not. But it's still need to look into that. All right, so that's pretty much it.
That's a whole lot of stuff. So, but it's, I mean, the concepts, well, you know, Ractor is a new word, new as of Ruby 3.0. The whole actor model has been around for a very long time.
Forever, yeah.
And these concepts of parallel processing aren't new. So this seems more like this is just trying to figure out the best implementation details for Ruby for this parallel processing paradigm.
Yeah, so here's the thing. I never engaged in multi-threaded programming because everything you read, you hear about people pulling their hair out, people hating it. It's really complicated and all this sort of stuff. And I started learning Elixir, which of course relies on, essentially it's all about these actors, these processes. That's their model of concurrency, is using this. I'm like, well, this is easy to understand. This is simple. And again, there's no real sharing. It's just independent processes passing messages between one another. So there's no like locking or mutexes or stuff like you have in Ruby and whatnot. So it's like, to me, it's the actor model is concurrency on easy mode.
Yeah. Well,
because it's easier for me to comprehend and understand. It's easy to make something that's not going to blow up And I think because it's not sharing state that you have to manage.
Yeah, and I typically stay away from this kind of stuff, conversations, the multi-threading and the parallel processing, because I spent a lot of time in .NET where there's a lot of multi-threading going on. And what I discovered is I spent a lot of time living in thread hell, and dealing with race conditions and trying to figure out how to troubleshoot and track issues that show up in production that you can't recreate because it just happens to be some specific clock cycle that happens that crosses these threads. And then so I got to a point where, oh my God, if I ever see another multi-threaded application, I'm going to quit programming forever. It's horrible. So I've kind of stayed away from that whole topic in my Ruby life, because I liked the fact that Ruby was nice and simple and straight. And, if I need to trace something, I trace it through in one thread and I can see where everything's going. But there's a lot of benefit to multiprocessing. I actually still, though, am sitting here wondering what this buys me that I can't do with something like Sidekick. Because I can effectively make this model in Sidekick.
What do you mean make this model?
Well, I can construct things such that, and we do this. My main thread has an event manager that calls events that basically spawn Sidekick jobs. And those jobs can spawn child jobs that can go off and run their thing while the main Sidekick queue, Sidekick queue A is doing its thing, calling Sidekick queue B that does its thing. And then when Sidekick queue B is done, it...
Well, I'll answer this from two different perspectives. So one, you don't have to use this in your programming unless you're wanting to do concurrent stuff yourself. So it's available to you if you want to do it.
Yeah.
So I'll say that's one part. The other part is the advantage of once this is no longer experimental, now you have an opportunity for Sidekick programmers to move to using this. And if they move to using this, could they avoid potential bugs from race conditions and their own programming of it for for concurrency? Instead of doing multi-threaded, they do multiple Ractors. And again, once this is no longer experimental, that means when you're spawning jobs, you don't have a single global VM lock for Ruby process. Now you can have as many as you want. Yeah. So that means you can, again, go full parallel. You can do 100% of a core when you're having all CPU process. You don't have to make the distinction. Are we waiting for IO or not?
Well, yeah, but you still have the potential for race conditions, and the more parallel you go, the more complex your code needs to be to prevent race conditions.
How do you have race conditions if you don't have a shared state?
Well, I mean, I guess it depends on what you're using the Ractors for, but if you're using them to, like I've run into situations, and I have some now, where I've got a big job, overall job, that needs to be broken down into small parts. So a lot of those parts are sent off to background jobs to process so that they can run in parallel, right? So I don't have to wait for each one to process. But I have to wait for those jobs to finish before I do final steps on this thing.
Sure.
If I don't wait for those jobs to finish and I do final steps on this thing before I have all the information from those sub jobs, I end up with race conditions. Like I have a null field here when I save this record because I haven't gotten the information back from this. I didn't wait for the field value to come back from, the sub job. That's a simplistic example, but that's the kind of thing that can happen with these. And the more of those I have, the more complex my safety net code has to be to ensure that I don't miss one of those things. They've all communicated back completion and successful completion. So I wonder if there are use cases that are better suited to this than others. Like you don't necessarily want to parallel process everything. Because troubleshooting that becomes a nightmare. It's an absolute
well, you don't
nightmare.
have to worry. You don't have to worry about it. It's just a different way of thinking when you're programming something. Because again, like in Elixir and Erlang, everything is essentially, you can make everything an actor. If you want to do a job, you spawn another actor, you send it a message, hey, do this work, and handle the result message however you want to.
Well,
so everything's built that way.
Well, that's all well and good as long as you're not dependent on the results of that child process you've spawned. As soon as you
can be.
Right, you can be, but then you have to make sure that you've got code that ensures you don't get race conditions when this thing doesn't finish. If B doesn't finish and I'm dependent on B to continue A better check that B is finished.
Well, don't finish A.
Well, but that's what I'm saying. You got to know not to finish A yet until B comes back. And those are the race conditions.
I don't know, but I don't know if I'd call it a race condition, but that's me.
Well, yeah, I mean, it's like database race conditions and programming race conditions, but let's call it a timing issue that we have to deal with.
No, I mean, you just have to wait for it to finish.
Right, which essentially is what caused all the thread hell in .NET. Making sure that you get the weights. Well, making sure that you get the weights all correct and that you don't miss something messaging back. I'm not saying you can't do it. I'm saying the more of those you have, the more complex the safety net code has to be. And also the more complex the troubleshooting gets. So
yeah, I mean, parallel concurrent programming, doing things in parallel, is definitely more complex than doing stuff serially. No doubt about it.
Yeah.
But I will say the actor model in my exposure, because I do have experience with it, but I don't have a lot of experience doing multi-threaded programming. But my exposure to the actor model and my experience using the actor model, it seems to be concurrency on easy mode. Because what it does is it protects you from accessing shared things you can. Because that's why I really like this, that what Ruby is doing. And that I hope we move to using this soon, because then it affords you protection that you're not going to be accessing shared memory and causing race conditions like you can with threading. Because you can build the actor model in a multi-threaded solution today. But the thing is, you're not going to get that independent global VM lock for that thread. You still only have one. So it still constrains you. Whereas the promise of the Ractors is a safer way to use all the resources of a machine, not when you don't have to wait on I/O.
Right.
And if things like Rails utilize this, if things like Sidekick utilize it, I think you're going to see a boost in speed performance of those products once Ractors are in there. Not to say they're going to be using Ractors, but I foresee them potentially moving to that and receiving a speed boost because of it.
Yeah, and I'm not saying Ractors are a bad idea or a bad thing, and I hope they keep moving forward. I mean, there is a reason to do multi-threading or parallel processing for things. I use parallel processing for testing, and then the whole reason a lot of people use the CI/CD systems is because they can spin up parallel testing regimens and make your test suite take 20 minutes instead of 4 hours. But what I'm wondering is, and again, I don't have any experience with Ractors. What I'm coming back to is, oh my God, this sounds a lot like multi-threading in .NET conceptually. Am I going to hate it as much as I did multi-threading in .NET? And just because, oh my God, I hated using multi-threading in .NET. It was just a nightmare every time.
Well, here's what I'll say. If you're not using Ruby threads today, you're probably not going to be using Ractors tomorrow.
Yay, then I don't have anything to worry about.
Yeah, so I mean, it's, again, if you use it, this is a new tool to use. If you never do anything, like a Rails programmer, unless they're going to be processing their own jobs in a separate way outside of Sidekick, you're not going to be using Ractors.
I mean, yes, that's true.
But this has benefits to using more resources of whatever machine you're running Sidekick on. So if Sidekick moves to this model, if Ruby finishes and Sidekick moves to this model, I could see now you get more bang for your buck out of the machines you're running Sidekick on.
Now see, if Sidekick were to use this underneath me and I didn't have to worry about those
implementation
details, I'd be a very happy camper.
Right, because what if you suddenly get a 25%, you can run 25% more jobs on the same server simply by moving from threads to Ractors.
Right, well, okay, so see that, if Sidekick were able to employ this stuff, and I know it's not ready for prime time yet, but if Sidekick were able to do this, that would be a huge benefit to me.
Yeah,
because it's incredible amount of bang for $0 in my case. I mean, we pay for Sidekick, but it's we don't have to invest the time into the implementation details of the multi-threading garbage and keeping that all straight, which Sidekick already has to do a lot of keeping things straight.
Yeah, that's what I'm saying. Yeah, I mean, that's what I try to answer my 2 points in terms of one. It kind of goes back to, if you want to do concurrent programming, this gives you an easy mode to do it. If you want to start doing, you don't necessarily have to do. If you don't do multi-threading today, you don't have to use Ractors tomorrow, probably. But secondly, the tools vendors, Sidekick, Rails, it gives them greater opportunities to do more processing, run more efficiently.
Yeah. So I guess I could see huge benefit kind of thing. Because honestly, as long as I've been doing Rails, I've never done any kind of multi-threading. The only parallel processing I've ever used is for my test suites. I've just never been in a situation where I needed to do that much parallel processing. Now I could see, with this big kickoff of like Ruby game programming and stuff like that, this would be a hugely beneficial to something like a game that has to do a lot of cycles in one type of function. Not necessarily a game, but that mode of programming where it's, I've got 3 queues, but I got to get 5,000 people through the queue every second. So, yeah, I mean, like I said, I think it's a good idea. I like the fact that technology is moving forward, and I'm interested to see where it turns out. I just don't see it for me yet. But hey,
But that's a great thing. It could be for everybody.
right. Well,
Because
I mean,
this has made me more excited about Ruby, because that's kind of why I started Elixir, because Ruby honestly is a dog. And then the promise of the concurrent programming and seeing what Elixir can do is kind of why I started learning it. Because I'm like, again, Ruby's demise has been communicated for many years.
yeah.
So, I was hedging my bets at one point. I said, oh, well, this Elixir stuff looks pretty cool. So I started, learning it that way. But this has actually made me more excited for what Ruby can do. So,
Yeah. And, I think it's helping to move Ruby forward. I think it's a good thing. Even if it turns out never to be primetime ready and this experiment somehow fails, I still think it's good steps in moving the technology forward. I mean, experimenting and failing is just as valuable as succeeding. So, not that I think it will, but I already see lots of benefits from a learning standpoint. But see how it goes. I think, honestly, I think Ruby is still on a good upswing, good glide path, and is only getting better. So we shall see. Anyway, hope you guys enjoyed that tonight. Thanks for being with us. If you have any questions or comments, please leave them in the comment box below. Also, please make sure and follow, like, or subscribe so that you know when we go live. You can also join us on our website, rubberduckdevshow.com, to see all our podcasts and episodes there, as well as join our newsletter. And you can keep up with what we're doing on Twitter. Follow us there at @DuckyDevShow. We are here every Wednesday night at 8 p.m. Eastern, so please feel free to jump in and join the chat live. We're happy to discuss things with you. And until next week, happy programming.
happy programming.